SpaceX is quietly positioning itself to achieve a milestone that has never been accomplished in the history of spaceflight, bringing an orbital-class spacecraft all the way back home for a fully reusable landing. While the space community has witnessed 12 Starship flight tests to date, some ending in flawless milestones, others in spectacular fireballs, and a few managing to do both, every single attempt shared a common constraint. The upper stage never actually locked into a stable, operational orbit before heading back down. That paradigm is about to shift. A newly uncovered Federal Communications Commission authorization outlines a mission explicitly described as a Starship Orbital Return Demo, launching from Starbase, Texas, signaling that this historic leap is closer than many anticipated. True orbital re-entry is an entirely different engineering challenge compared to a suborbital test trajectory. The vehicle must endure exponentially higher kinetic energy, severe thermal loads, and drastically increased atmospheric entry velocities. Every system on the spacecraft, from the heat shield tiles and flight software to the aerodynamic control flaps and engine relights, must perform flawlessly, as even minor issues can lead to catastrophic failure. The regulatory paperwork establishes an operational window from July 29th through late December 2026. Because SpaceX leadership has indicated that Flight 13 is targeting a July liftoff to continue suborbital vehicle validation, Flight 14 stands as the primary candidate for the program's first true orbital mission. However, a successful orbital return does not automatically mean a recovery at the launch site. SpaceX typically introduces operational complexity in gradual phases, meaning this initial demonstration will likely target a controlled ocean splashdown to master atmospheric survival before attempting to catch a returning ship with the launch tower. Concurrently, SpaceX is preparing to revive its spectacular mid-air booster recovery maneuver, which has been absent since the successful catch during Flight 8 over 15 months ago. This return to tower recovery will be spearheaded by Booster Phi 3, a heavily upgraded iteration of the Super Heavy first stage built for rapid airline-like operations. Moving away from experimental configurations, Booster V3 features a foundational redesign, replacing the standard 4 small grid fins with 3 larger, more robust units positioned lower on the chassis to escape the punishing thermal environment of hot staging. In a highly efficient structural optimization, the mechanical catch points have been integrated directly into 2 of these grid fins, eliminating separate catch hardware, shedding vehicle mass, and removing critical structural failure points. These enhancements are mirrored on the ground by the Mechazilla launch tower, where the giant chopsticks have been shortened for agility and upgraded with fast electromechanical actuators instead of hydraulic systems, effectively broadening the physical catch window to tolerate wind deviations and thrust anomalies. Beyond its Texas testing grounds, SpaceX is aggressively scaling its global infrastructure to support unprecedented launch cadences. At Vandenberg Space Force Base in California, the U.S. Space Force recently executed the demolition of the historic, unused infrastructure at Space Launch Complex 6. SpaceX has assumed control of the legacy footprint for an 18-month redevelopment project designed to transform it into a high-capacity Falcon 9 and Falcon Heavy complex. The ultimate goal is to support up to 100 launches per year from the West Coast, complete with dedicated coastal landing zones that will eventually allow spectators to witness synchronized dual-booster landings along the California shoreline. This rapid expansion of commercial launch capability directly underpins humanity's next steps toward the moon. Astrobotic has officially unveiled its new infrastructure-class robotic lunar lander, Griffin 1. Bouncing back from a propellant leak that compromised their Peregrine mission in 2024, Astrobotic has designed Griffin 1 to carry a substantial 625 kilograms of cargo. Scheduled to launch aboard a Falcon Heavy in late 2026 as part of NASA's Commercial Lunar Payload Services program, the lander is currently undergoing rigorous environmental testing at the Jet Propulsion Laboratory. It will transport 10 distinct payloads from 6 nations, headlined by Astrolab's highly anticipated Flip rover, acting as a cornerstone for building a sustained human and robotic presence on the lunar surface. From orbital re-entries in Texas to massive pad overhauls in California and heavy-duty landers bound for the moon, these interconnected milestones are actively rewriting the boundaries of modern aerospace engineering.